Well, we've talked about the boundary conditions at an interface that involved a charge sheet. Now I'd like to look at the interface between a conductor and vacuum. And so we'll look at the boundary conditions at that interface. We're going to use the boundary conditions we've already developed, and this was for the interface involving a charge layer of charge density sigma. And we're going to use principally this condition for conductors, that E inside is equal to 0. And we'll see if we can combine these to derive the boundary conditions for a conductor-vacuum interface. Well, so here we show the derivation that we used for determining this boundary condition. That involved using Gauss's law above and below and finding that the perpendicular component of the E field above minus the perpendicular component of E below was equal to the charge density over epsilon 0, where this sheet of charge has a density of sigma. We're going to use below for the metal. Sigma represents the charge on the surface of the metal, and we know that inside the metal, E inside is equal to 0. So we're going to take the perpendicular component of E, set it equal to 0, and see what happens. Well, that means we set this term equal to 0, and so we're left with the E perpendicular above the charged surface is equal to sigma over epsilon naught. So that's stated in words right here, that E perpendicular outside the conductor is sigma over epsilon 0. So that's a very useful result. Okay, so let's look at the difference between the charge sheet and the metallic surface. This quantity here differs from the non-metallic charge sheet by a factor of 2. So remember that E in that case was sigma over 2 epsilon naught. You might think of it this way, that this is half because half the field lines go on one side and half go to the other. Whereas for the metal, the charge on that surface simply takes field and goes in one direction only. That's one way to remember how these two compare. What about the parallel components? We use this path here to prove that the parallel component of E above was equal to the E parallel below. And that resulted from the fact that if we take a path around a closed loop and integrate E over a line integral over this path here, we'll get 0 because the path is closed, and to conserve energy that will be 0. And then using this dimension here very small and this dimension very close to the surface and not very large, we quickly came to the conclusion that having that go to 0 required that the parallel component of E above and below are equal. So let's go to the case where we have E inside equal to 0. So that means that E parallel below is 0. Both of these components, the E perpendicular and E parallel below the surface, which is inside the metal, are 0. That means that this quantity here equals 0, and so we can end up then that the parallel component outside the conductor equals 0. We can now combine these into a total E field at a metallic surface. If we add E parallel to E perpendicular as components with the unit vectors, then we'll end up with the conclusion that the outside E field, the vector E, is equal to sigma over epsilon 0 times n hat. There's a couple corollaries here that basically the direction into or out of the metal surface depends on the sign of sigma. If this were a metal surface and sigma was plus, then we would expect the field lines to go up away from the surface. If this were negative, the opposite would occur. You'd be coming into the surface like that. The other corollary is that E outside is always perpendicular to the surface, and that means E right at the surface, just outside of the metal. And that doesn't matter if there's a sigma or not. That is the result. So let's look at the potential. We'll take the derivation that we use for a charge sheet. To do that, remember, we took a very small path. It was just a distance slightly above the charge sheet and slightly below. We know that the difference of potential above and below is equal to minus the integral of E dot dl from A to B. But we know that if we let this distance go to very small intervals, so if the distance a to b is vanishingly small, then this will go to 0. So if this is 0, then the potential above equals the potential below. And I've written that here. Again, this is not dependent on the presence of charge. Therefore, the potential is continuous across the charge sheet. Let's imagine that you have a charge sheet not metallic, but you have these V above and V below, and we've already stated for the general case that this is the V above equals V below. Then we've done a problem that is useful for illustrating that, and that is that you have a finite line of charge of length L, and you're finding the potential at some distance Z. And if you remember, it's equal to this equation here. And if we put absolute values of Z for the value of Z here, we're getting the results for both sides of the sheet, so the plus direction and the minus direction. Well, this is what the plot looks like. This would be V, this would be Z here in both directions. And you'll notice that what happens is, of course, as you go up towards the charge sheet, this climbs, but it goes to a finite value. You can see, I don't know if you can see very well, but that's the top of this curve, right at Z equals 0. Of course, when you go the other way, it has to go down because you're going further and further away from this plus charge. And in fact, if we go far enough, it looks like a positive point charge. This is the Mathematica for the plot. So here's the function, and then we set the constants that we don't know equal to 1, and then plot it. And that's what you see here. Alright, now I want you to look at the potential right at the point where it hits 0. That's where the charge sheet is. Well, notice that they're equal on both sides. So in other words, you have a continuous V, even though it radically changes. So in other words, it's coming up and then bang, it's coming down. Right at that peak, you're having a very rapid change in V. But the point is, they're equal on both sides. That's an illustration then for a charge sheet. The potential across the interface of a charge sheet is continuous. Let's now go to a metal, and I've just repeated the arguments that we had above for this condition here for the charge sheet. For a charge conductor, let's say it has a surface charge sigma, and we'll take below to be inside the conductor. The same is true, that you have V outside the conductor surface is equal to the V of the conductor. And the argument is exactly the same. There's nothing here that is negated by the fact that one part of the problem is inside metal. So this equation still holds if we make the distance from A to B very, very small. And so as a result, we have the continuity of V between the metal and the outside right above the surface. Remember that V inside is a constant. Let's say it's V0. Then V outside the conductor is also equal to V0. Going from inside outside, we have the same potential. So if you had a battery, let's say the voltage of the battery was delta V, this conductor here, say, would be at 0 volts. This one here would be at delta V volts for the potential of this conductor. So if you're outside of this conductor right nearby, you'll get 0 volts for the potential. If you go over here just outside, you would have delta V volts for the potential right here. That gives us the effect of this continuity of the potential inside the conductor and just outside, inside the conductor, just outside. You know, if you were to guess right in between what that potential would be, depending on how smooth or how big these guys are, a good guess would be delta V over 2, somewhere in there. Okay, so let's now look at the gradient of the potential. We're talking about the gradient of the potential at a metal surface with a surface charge density sigma. For that, we start with our general boundary condition for the E field. So we have E above minus E below is equal to this. And we showed that if we just use the gradient in the normal direction at the interface, that we end up with this condition here, that the derivative of the potential above with respect to the normal variable that gives us a distance away from the interface minus the delta V below with respect to this coordinate is equal to minus sigma over epsilon naught. And so we got this by using the fact that E above is minus this quantity here, this is minus this quantity here. And by the time you take care of all the signs, you'll end up with a minus sign here. This is the boundary condition in general for the gradient. And just to remind you, n is the coordinate perpendicular to the surface. Note that this is a scalar relation, and also note that it's very sensitive to the sign of sigma. And this is a cause of great confusion when you're talking about these types of interfaces. For a metal, the interface with a vacuum, V below is a constant. If you take the derivative of that, you'll get 0. The derivative of the potential below the surface inside the metal is equal to 0. The derivative of V with respect to n above, so out in the vacuum, is equal to this quantity here. And again, notice the minus sign. This is the condition that you have for the potential at the surface of a conductor. Well, here's an illustration of that. Suppose over here you have a metal and you have a surface charge layer here. We're just guessing what the potential would be, but we know that it would fall as we get away from this surface charge. It would be like the partial line charge that we talked about. So here's the normal vector, and in this case here, the normal vector, the parameter or the coordinate is equal to x. The unit vector is also x hat. So for sigma greater than 0, then we would expect the potential to have some kind of behavior like this. Inside, we have a potential that's a constant. If we require that these be continuous, you'll notice that this one starts falling exactly with the same value V0 here. So this is a reasonable representation of the potential of a charged layer on a metal. So now let's look at these derivatives. This one here is the derivative of the potential above the metal, which is this one right here, with respect to the normal coordinate, which we've said is x. It's also equal to this quantity here. By the interface boundary condition that we derived, this should be minus sigma over epsilon naught. And that's less than 0 when you have a positive charge layer. Well, look what we have here. For the potential as a function of x has a negative slope. And so all of this is consistent in the sense that this negative slope and the relationship between the slope and the charge density are in fact consistent. Okay, so now let's look at the arrangement where we have a parallel plate capacitor, and we're going to look at these gradients that we just discussed. So we've already said that the E field is equal to this, sigma over epsilon naught times the unit vector, and that resulted from E inside equals 0. This E field outside the metal means that the E field just outside is in the gap. So we're talking about now, here's our parallel plates, separation D. The normal vector that we'll start with is on this surface here and is in this direction, and we'll take that in the positive x direction. So if this layer is plus and this layer is minus, then the E field shown here is in this direction here. So it's in the minus n hat direction. All of this comes about because we applied a battery across the two plates. To nail down this potential, we've grounded it. So this is 0. This potential here is 0. This potential on this plate would be delta V. That's the battery voltage. And of course, E equals 0 inside. So what does the potential look like? Well, we know that this surface is 0, and this potential here is delta V. So up here is delta V. And that occurs when we've gone to a distance d. So here's 0x, here's x equal d. That's this value of x right here. We know that with a constant E field, which is the case when we have these parallel plates, the potential will just be a linear function of the distance until you hit the plate, then it'll be a constant delta V. The E in the gap is just outside of the surface of the metal, and we note that that is perpendicular to the surface. So for the charges that we have here, if we take this to be a positive number, then the E in the gap outside of the metal is equal to this quantity here. That's the value at the interface, and it's also the value inside the gap. So on the left-hand side, where we have negative charge, the E field will be in the minus x direction, where x hat is in the n hat direction. So right here, if this is n hat, then the E field right here is in that direction there. And realize this point is outside into the gap. And this E field and this E field are equal. Okay, so let's talk about the potential, and we'll talk about it over here and this point here. If we have a V of x, what we are trying to do is confirm this quantity here, that the partial of V outside with respect to the normal coordinate will be minus the sigma over epsilon naught. So we've already said that this is a linear function, and if you go through the derivation of what this would be, it would be a change in voltage, the battery voltage here, times x over d. When x equals d, you get the battery voltage, and that's this right up here. And so this function starts at x equals 0 at 0 and goes up to delta v. And don't forget that coordinate n and x are the same. If you look at the fact that you've got this behavior of voltage as a function of x, we can take anywhere in the gap, we can take this derivative. So this would be like taking this derivative here. So putting in the potential, we'll basically get this quantity here for the derivative of v with respect to x or with respect to n. So delta v is a constant, and you have the derivative of x with respect to x. That gives you a 1 times delta v, gives you this quantity here. Well, this includes the position x equals 0. So at the left plate, we're still in the gap, and so over here on this plate right here, in the gap, we still have this relationship. But now we're going to use capacitance. So here's the capacitance of a parallel plate capacitor, which you're familiar with. But C is equal to Q over V. Now remember, this is a positive number here. So if we're going to do that, then at the left-hand side, where Q is negative, we have to use a minus Q in order to make this positive. So Q is negative, minus Q will be positive. So if we put the capacitance here equal to minus Q over V, then that will be sigma A, which is Q, divided by delta V. So then we take positive quantities for both Q and sigma, and we solve for delta V over D, and we get this result. Delta V over D is equal to minus sigma over epsilon 0. But delta V over D is equal to the left-hand side of what we're trying to show. So coming down here then, and putting that in, we end up with the partial of V with respect to the coordinate that is perpendicular to the surface from the metal to the gap will give us this quantity right here. All we've shown is that we get an agreement with the boundary condition for the gradient for this situation where you have a battery hooked up to these parallel plates, and so far we've just talked about what's happening over here, and we've shown that this in fact is the case. So now let's look at the other interface over here on the right hand side, and just to remind you, for the left hand side we found this expression here for the derivative of v with respect to n, and that was delta v over d. And so that put the situation where the origin at the surface of the left-hand side plate is over here at O. Now we need to turn the n direction around because we're going to put the unit vector on this surface over here. Going from the metal to the gap is in the opposite direction here. So if that's the case, then what we're saying is V above is on the left, V below is on the right, the reverse of what we had before. If we do that, then we have to turn this potential delta V over D around. Remember, this is positive, but if you look here, we're going from a case where we're at this potential, and then as soon as we go outside it comes down. So that slope is negative, and so that's why we have to put that minus sign there. Well, after you do this, then it's just coasting because you start with your capacitor equation here, same equation for the capacitance with respect to Q and V. C is positive, but on the right hand side, Q and sigma are both positive. We don't do any changes of sign here. So then you rewrite your capacitance here in terms of the surface charge density. Q is sigma times A, V is delta V, and because these are positive, we just leave this alone. We can solve this for delta V over D, and so that will be equal to delta D over V turns out to be sigma over epsilon naught. So if we change the sign, then this will be minus sigma over epsilon naught. Remember up here we had this expression right here, delta V outside with respect to n is minus delta V over D. So you can see then that we can set this derivative equal to minus sigma over epsilon naught. So in this case here, when we're over here, we have this delta H over n is going from this slope here to this. So the gradient, or the derivative of V with respect to n, is going to be positive. Over here, it's going to be negative. The only difference between viewing it here and here is the direction that you're changing. So you're changing the direction of the normal vector. But if you keep that into account, if you're taking the derivative of V above with respect to a coordinate that's going this way, then you'll get the expression minus sigma over epsilon naught. Sigma is positive, the slope is negative, so that gives you the correct sign for this relationship here. And I think you can see that if you argue over here, that change will be positive. But in this case over here, where we had the final expression being minus, that came because we were at a minus q on this surface here. So that changed the sign right here. That changed the sign of q, and so therefore we end up with the minus sign.